Let's move on to question 5. Question 5 is an important question because this is what we call the knapsack problem. Knapsack problem is a traditional knapsack problem, which is a combinatorial optimization problem. We use the word bag in the question, but basically it's the same as a knapsack. Now, idea here is you have got certain n number of items, and each item has a weight and a value, and you are allowed to put in any combination of items into the bag or the knapsack. The objective is to maximize the value. And yet, there's a constraint. The constraint is the total weight must not exceed 15. All right, so must keep in mind the objective of your algo and the constraint, which needs to be respected. All right. Now, for this particular question, there's only one item A, there's only one item B, one item C, and so on. So you can only choose one A. Okay, if you want to choose A. There are some other questions. There are multiple multiple A's and multiple B's and so on. So look at the question very carefully. In this case, there are only 5 items. You can select any of these 5 or none of these 5. So let's go to Q part A. Part A. Design a brute force algo to determine which item or items to be put into the knapsack or the bag. Now, basically, brute force simply means you want to try all possible combinations. So you have one item combination. There are 5 such combinations. There are 2 item combinations. There'll be 5. Choose 2 such combinations. There are 3 item combinations, 4 item combinations, and there are 5 item combinations, of which there is only one. 5, choose 5. All right. Probably a better way to do this is, you can list these 5 items here, A, B, C, D, E, and each row here represents a combination. All right. 0 means exclude, 1 means include. So I have 0, 0, 0. This particular combination will exclude all. That means it's an empty bag. Obviously not a good answer, but anyway, it is possible. There are some situations whereby none of the items can fit in. So this row means only E is selected to be put into the bag. This row means only D is selected to be put in the bag. This row means 1D and 1E goes in, and so on. This row means only C goes in, and dot, dot, dot. This last row means all 5 items go into the bag. Now, for each combination or for each row, you can give a score. In this case, the score is going to be the sum of all the values. All right. Okay. The weight is going to be 0 as well. This one, the score is going to be the $6 because E is $6, and the weight is going to be 2 kg because E is 2 kg. This one is going to score $5 because D is $5 and it's going to cost 3 kg. This will be 1D and 1E. 1D and 1E will be $11 altogether and 5 kg, and so on. So for each combination, you have to score it using a function, a scoring function, which is not difficult to write in this case. And of course, you have to compute the total weight. Again, it's not difficult to write a function which computes the weight. Now, here, there are certain weights which are above our constraint of 15 kg. That means more than 15. And we're going to exclude all those. So there are some rows which are valid, some rows which are not valid because of the weight. Of all the rows which are valid, we'll actually select the row with the largest score. In this case, we want the score to be as high as possible. In some contexts, where you want the score to be as low as possible, you have to read the question. So we'll choose the row of the highest score. Sometimes there can be more than one, there can be multiple rows of the same highest score, in which case there can be multiple correct answers. And that is the answer. Now, brute force will guarantee the real optimal answer because you are trying all possible combinations and scoring each one. Okay, so how many possible combinations are there? Basically 2 to the power of n, or in this case 2 to the power of 5. There'll be 2 to the power of 5 rows in this table, or 32. Not too big in this case, but if n goes up higher, this problem is going to become 2 to the power of n. We have to try 2 to the power of n combinations, and The time complexity will depend on the number of combinations times the cost of the scoring algorithm, the scoring function. Let's move on to B. B, design a greedy algorithm to determine the items. Now, greedy algorithm, no guarantee that it's going to produce the optimal solution, but well, something close enough, not bad. So, well, there are a few ways you can write a greedy algorithm. Okay, the first algo will be greedy by weight, okay, by value. In other words, we will actually select, during each iteration, during each step, we will select the item with the highest value. What's the basis for this? The idea is we want to actually choose items of the highest value to be put into the bag first, so that in the hope that the total value will be as high as possible. Okay, so basically sort by value. In this case, we want highest to lowest by in descending order. We want the highest value item to have the highest priority. And then for each item in the list, we will actually do this, okay, check if the current current weight of the bag plus the current item's weight is small or equivalent to our constraint, 15 kg, we will want to include it. Okay, put this current item into our knapsack, and then we move on. Right. Using this algorithm, let's see what's going to happen. Now, let me sort by value quickly in descending order, sort by value from largest to smallest. Okay, we want item A because it has the highest value. So item A will have the highest priority. So now in step two, we will look at item A and the weight is below 15. So yes, please insert A into the knapsack. Then next iteration, we look at item B. Cannot insert item B because it's going to bust my budget. It will become 17, which is bigger than 15, so ignore that. Move on to item E. In the third iteration, item E, yes, please insert because 12 plus 2 is 14, good enough. Next iteration, item D cannot. If you try to insert D, it will bust the budget. And then next item, C also cannot. Okay. So the solution will be A and E if you use this algo, and the value will be A's value 10 plus 6, 16. All right, I'm going to cover the next greedy algorithm. It's exactly the same thing, but this time around, we are going to change the selection criteria by weight. Now, the idea here is if we actually choose an item based on weight, we want the weight to be as small as possible. We want to choose items of a small weight so that hopefully more items can go into the bag. And the assumption here is the more items go into the bag, hopefully the total value of the items will shoot up. Okay, of course, that is an assumption. In this case, I'll sort by weight in ascending order. That means the smallest weight will have, the item with the smallest weight will have highest priority. Let's quickly do this now. Data weight, sort by weight. And we want smallest to largest because the smallest weight, the item with the smallest weight will have the highest priority. Okay, in the hope that more items can be packed into the bag. So let's go through the iteration in step 2. First iteration, okay, insert this E because the weight is good. Okay, next iteration, I'll insert D because 2 plus 3 is 5, good enough. Okay, third iteration, insert C, yes, because 5 plus 4 is 9, good enough. Total weight now is 9. Fourth iteration, 9 plus 5 is 14, good enough, so I'll still insert B. And last iteration here, I will not insert A because you have busted my budget if I do that. So total value here will be the sum of this, okay, which is $21, which is fine, okay, $21. The third greedy algorithm, okay, again, is very similar to the first two, except that now this time I want to, the criteria is value over weight. It's a ratio, value over weight. sort by value over weight in descending order because I create a new column here, value over weight. Okay. Basically D26 over C26. Now the idea here is we want an item with a highest value over weight ratio. The higher the value over weight ratio, the higher the value, right? That means for the same weight, 1 kg, I have this amount of value. Okay, quickly sort this table in descending order. Okay, value over weight descending order largest, so that I will prioritize item E. Okay, item E, the value is $3 per kg. So how will the solution look like? Item E will go in because during the first iteration, the weight is below 15. During the second iteration, I will insert D as well, okay, because now the total is 5 kg. Then third iteration, I will insert B because 5 plus 5 is 10, which is still good. Fourth iteration, I cannot insert A because 10 plus 12 is 22, which will pass my budget. So last iteration, I will insert C. Yes, I'll insert C because 10 plus 4 is 14, still within budget. Insert C. So this will be my solution. And you realize that in this particular case, the value is going to be 21 as well. Actually, it's the same answer as the second greedy algorithm, just that, order is a bit different, but doesn't matter. Same 4 items will be inserted. Okay, so these are the 3 greedy algorithms. Intuitively, you will think that the third greedy algorithm, this one, should work better than the first 2 because both weight and value are taken into consideration, but there is no guarantee that the third greedy algorithm will produce a better result than the first 2. It really depends on the data set given. All right. So let's go on to part C. For the above 5 items, is there any weight limit for which greedy fails to find the optimal solution? Yes. And we're supposed to come up with there are many possible answers, but one possible answer will be 7 kg if we use the third greedy algorithm. So let's quickly copy the third greedy algorithm over. Okay, so the only thing which has changed is the constraint. So instead of 15 kg, I'm saying, okay, your bag cannot exceed 7 kg. And using the same 5 items, let's see what will be the solution here. The solution will be, during the first iteration, I'll consider E and E will go in. Yep. Okay, the total weight now is 2. Second iteration, D will go in. Okay, the total weight now is 5. All right. Third iteration cannot insert B. Okay, because it will pass my constraint of 7 kg. Next iteration cannot insert. Next iteration also cannot insert. All right, too bad. So my solution is going to have to be E and D. The total value of E and D will be only 11. 6 plus 5. All right, and this is not the optimal answer. The optimal answer, because this data set is small, I can eyeball, and I can tell quickly that if I choose E and B, quickly E and B, I'm going to get the value of 14. All right, which is bigger than the solution, which this third greedy algorithm will give. So of course, there are multiple correct answers. You just have to find one weight constraint for which your chosen greedy algorithm, be it the first, second, or third, or even your own greedy algorithm, fail to find the optimal solution. That's it.